Section 21.5, the chemistry of anhydrides. So again, here's our anhydride. This has had water removed from 2 equivalents of a carboxylic acid. The mechanism of substitutions here is like before. I've got a fundamental illustration here, not a complete mechanism. Again, we have nucleophilic attack on the carbonyl. We form a tetrahedral intermediate. And that tetrahedral intermediate, of course, then undergoes some changes and eventually eliminates to give you the amide. In the case of anhydrides, we have the carboxylic acid that's formed there, so we don't need so much the 2 equivalents that we had before, because we'll have a different product here. You start with that one, since we have that carboxylic acid. And the same thing will be true here, because we have the formate, or the acetate in this particular illustration. We won't need that second equivalent for those amines. So let me start with the amines here. The carboxylic acid, we can, with many amines, the key is we've got to have a hydrogen, so tertiary amines don't work. We can produce the amide in a very straightforward and efficient manner. This is also highly useful for making esters. Again, we want to use a tertiary amine base with this. Typically it goes a little faster. I won't get into all the details of why that is. It has something to do with nucleophilic catalysis, and we can form the ester. Now, unlike the chemistry of acid chlorides, we're not going to make mixed anhydrides from anhydrides. It's just a messy equilibrium. We can hydrolyze them, so that chemistry will work. We can reduce them. Again, lithium aluminum hydride, it won't stop, and in fact we would get 2 equivalents of the alcohol here. We don't do Grignard or other organometallic additions to anhydrides. That doesn't work as well for these. So again, in a nutshell, that's 21.5 anhydrides.